we need to get some things established so you guys can have homework 9 turned in. So we left off with force equals I L cross B. And we were doing things where we wanted to figure out what the forces were for this or that, and due to a magnetic field. Okay, so I'm just going to redo this. We have an current. We have a current I, and it's going in that direction. If it is, we use the right-hand rule to figure out what the B field is doing, and you put your thumb along the current, and then your fingers point in the direction of the B field. So into the page and out of the page. Okay, so just put your thumb along I and you can see that. All right. Now, we talked a little bit about it, and we looked at a circle, for example. So you have a circle with current flowing, and if we have a B field that is going, say, like this, then the top half of the circle has current going there, current going there. It's different, right? So let's just look at this one spot, and we'll look at this one spot. And we'll do I cross B. So now you put your fingers along I, you cross it with B, and you notice that your force on the top is into the page. Then you do I at the bottom, put your fingers along I, curl them toward B, and your force is coming out of the page at the bottom. So what does that do for this thing? Well, it puts an axis right down the middle, and it wants to spin, and that means that there's some kind of a torque, okay? And the torque wants to spin this thing. So that's exactly what we're going to talk about next, is torque. So torque. Let's lay it out. Let's draw out a B field. Okay, now imagine the whole page is B field in this area. Okay, now let's make it a little bit longer so we have some ability to do some things here. And okay, so that's our B field. Let me put a vector on there because it is definitely going in a certain direction. And now we can do this thing where we say we've put this thing in our B field, and we're going to run current through it. Okay, so maybe we'll go up one side and down the other with our current. So we'll have some DC source, down here driving our current. At the top, the current is going this way, and at the bottom, of course, it's going this way and going this way. Okay, so we already know that our force at the top and bottom, so I'm going to write top, bottom, that force is equal to IL cross B, but if I and B are in the same direction, that's going to end up being 0. So our contributions from the top and the bottom are 0. And we really only have the contributions from the sides giving us our torque, okay? So we have to kind of say, all right, well, what is our distances about this center axis? Okay, because that's the center axis is where this thing is going to get rotated about. And if we say that there's a distance d from the center to the outside, kind of like our radius, then the whole top is 2d. Software isn't the greatest, but it works. Okay, so that's fine. Let's do the torque on one side only, okay? So let's do our torque is equal to d cross F. So now we need to figure out what F is, and we already know that F is equal to our I L cross B. So should we do the right side? Let's do the down side first. So the right side. All right. And our force is whatever the current is, and everything's perpendicular to each other, right? This is a 90-degree thing. So then our force is, I guess I'm going to make this L from here to there. Okay, so good. Whatever that L is, that's fine. Our force, everything's 90 degrees, so the sine of theta goes away to 1, goes to 1, and we'll just say ILB. Fine. Well, this force, what direction is it in? We're going to put our fingers along I, we're going to curve them toward B, and our force is toward us. Okay? So now we figured out which direction the force is, and we've got D, and our D is pointing in this direction. So D cross F is going to give us a torque, and that torque is down, D cross F, right? So our torque actually points in this direction on the right side. Okay, so should we label coordinate system? Okay. So we'll just say that our torque is equal to, and it's all 90 degrees. All these things are 90 degrees, so the sine of all the angles is, and we'll say negative j hat direction. And I said negative I hat, but I want j hat. Okay, that's the right side. Well, you can guess that the same thing's going to happen on the left side, and now all we have to do is figure out our direction. So first, what is our direction of our force? I cross B puts our force down like this. Our force is going down on this side. So this is the force on the left, this is the force on the right. And then, of course, our D is pointing in that direction. So when we go to do D cross F, we have D cross F, and it's also pointing. So this is on the right side. Our torque is pointing down on the left side, which is also minus J. Now, the whole thing is a system, right? So we're really going to be adding our total net torque is going to be adding our torque from the right plus our torque from the left, and that leaves us with 2 times D times I, L, and B. Okay. Now let's put back. You know what? I'm gonna make some room for myself here. Let's put back our sine theta between I and B. Okay, so we're gonna put back. Boop, 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 boop. We're gonna put back this sine theta. So why are we doing that? Because the D is always going to be the sine of the angle. So let's say the angle between D and F. That's always 90 degrees. So we can call that angle phi and say that the sine of phi is always equal to 1. So this part is always going to be D times F, okay? But our torque, so we've got dF, but we still have F is IL cross B. Now here's the thing. This thing's going to rotate in B. So as it rotates, I cross B, is that going to change? None of this is going to change. I cross B. Our I is going down. It will always be going down, and it'll always cross B. I was wrong. I'm sorry, guys. Wrong. It's not this. It's not this one that is the one that changes. It really is D. So at sometimes D and the force are going to, the angle between D and the force is going to give us this sine of phi, okay? So we really end up with our torque is equal to dF sine phi, and IL cross B is always going to be, I cross B is always going to be sine of theta is 90, sine of theta is 1. So our torque then is D I L B sine phi. Okay, at all times. So there will be times when D and F are in, it's in line with F. D is in line with F. So there will be times when our torque is 0, okay? And that will be when the loop is perpendicular to the B field, but also parallel with the forces that are generated. Okay, good. So let's look at this. Let's look at this thing. I'm going to draw it a little bit bigger. And without the B field in our way. And so here's our area. This is D. So our area A is equal to 2D times L. Okay? And this thing is spinning in the B field, which is going to the right. So let's put a B field down here. But this time we're looking at the B field, and I'm going to put this thing that we've got spinning in the B field, I'm going to put it like this. Okay? So we're looking down on it from this direction. Okay? So that's our view. Down from the top. So what is the normal to our field? Our normal to our area, I should say. That's the thing that we care about, the normal to the field. So our field is B here. We've got our normal there. And of course, the angle that we then care about, this is our angle phi. Okay? So that's nice, right? So now we can then say, okay, well, really our torque is dLIB sine phi but our area is equal to 2dl. Oh, and I dropped a 2 somewhere. I dropped my 2. Gotta have the 2. So 2dl, this is our area. So we can say that our torque is equal to area times IB sine phi. Cool. That is, that's a great closed loop situation. Now, okay, I showed you that in our case, that the torque pointed down. Okay, and that's true. All right. The thing, though, happens to rotate clockwise or counterclockwise, depending on which way the current is flowing. If we're looking top down, this side would have current going into the page. This side has current coming out of the page. So, boom, boom, boom. Which way is our force going? So our force is current cross B. So I've got my current cross B, so the force is going here. And on the top part, it's coming towards us, and our force is coming there. Perfect. So those are our forces, and great. That's fine. And then as this normal shrinks down, it's going to come this way and shrink phi down to a point where it doesn't want to move any further because the forces are pointing the way that they would like to. But momentum will keep this thing going, and once the momentum keeps it going, it'll straighten back out. We'll talk about that in a second, what we do in that situation. So you can look at it as going clockwise, and then you can say, okay, well, I want it to be clockwise positive and counterclockwise negative. Counterclockwise negative. You can do that. And then you're really not worrying about which direction the torque is technically pointing in, because I don't know if that really matters. You kind of really want to just know which way it's spinning, right? So even though the torque is definitely pointing down, we don't care about that. We just want to know which way is it spinning. Okay. So we call this closed loop, all right, this closed loop. So I'm going to draw it again. Closed loop. This is called a magnetic. Better put some current in it. Dipole. And it has a magnetic dipole moment. And so we say, all right, mu is the magnetic dipole moment. That mu is defined to be the current times A in the n hat direction. Okay? So if that's the case, then we easily can substitute in IA n hat, and we'll get that our torque is equal to our magnetic moment times B, or better yet, let's just do our magnetic moment cross B, okay? And then whatever that angle between N and the B field is our angle phi, or theta, or whatever angle you want to assign to it. Now, that's all fine and good, but we've got one other thing that we can do, and that is create multiple loops. So we have our current come in. Now let's just draw it as a circle, okay? So we draw it as a circle, but the circle continues. And we go around in a circle like this. And then we have this come out. So how many circles do we have? N circles. In our case, it's n equals 4. So our torque now is equal to 4 times that, or 4IA n hat. So good, but what we're going to do is replace mu, instead of IA, it's n for the number of turns. Okay, so mu is now n I a n hat. And then you'll have the same equation, mu cross B. And the case here, this case, just happens to be the case of n equals 1. So mu cross B, that is our takeaway from this. So all we really have to do is learn about what is mu cross B. I'm going to just do this without any proof. There's no the proof isn't terribly hard. Maybe I'll turn it into a homework assignment. I don't know. But our energy for the system, you guys, I don't know if you remember. I'm just going to do this real quick. So torque is RD cross F, right? And the D's in meters, newtons here. And I said in my course, we talked about meter newtons being the unit for torque, okay? And I don't know if you guys remember, but work is equal to D dot F. And that is also, I call it Newton meters instead, okay? So Newton meters, what is that? That's a joule. But a meter Newton is not a joule, okay? But it kind of is. It's still like an energy. And if you think of it that way, if you're doing the dot product, you get the energy, U, potential energy equals U. And we get the dot product. So if we take, oh boy, if we take our minus mu dot our B field, then we have our energy. So the dot product leaves you with this. The cross product leaves you with this. So when you do the cross product, you end up with meter newtons. I think it's just better to keep it meter newtons, right? It's foot pounds. Think of it, torque, foot pounds, meter newtons, okay? And then in this situation, we end up with joules, which is our energy, okay? So it's a dot product, which means that it's minus our mu B, and then the cosine of the angle between them. So that is equal to our potential energy. So minus mu B cosine of phi. All right. Let's continue with the Hall effect. All right, so we have a strip of metal with current I going through it. So our strip of metal isn't just a wire, it's a flat wire. So we have a flat wire strip of metal, and there's some length here. I'm calling it length, but it's technically the width, but whatever. And on the top side, no. Forget that. Let's do, let's just lay down what our B field is doing. So our B field is going into the page. And we'll have some current, okay? How do I want to do this? Let's put our current, oh, I don't want current like that. I want current like this. Here's our current. Okay, so the holes are moving from left to right. The electrons are moving from right to left. So if the electrons are moving from right to left, and the protons are moving, or the holes are moving from right to left, the electron's moving left to right. We put our fingers along the current, we curl them to the B field, and our force is down. But the electrons are going to the right. Their force is also down. And that's the real thing. The force of the electrons is down, and they're going to create this negative on this side. Believe it or not, the holes go to the top side. And do I want to get into that? Okay. We've got this going there, cross there. Do I have it backwards? I have it backwards. It flips. Darn it. It flips. My mistake. So the holes end up taking it and making it positive here. My picture in my notes is wrong. And this is the negative side because the force flips because of the charge. Positive charge, negative charge. And we'll have this thing that develops. Well, what does this create? It creates an E field, okay? And our E field goes from positive to negative. Come on, baby. Positive to negative, E field. Just because we have our current flowing in a B field, okay? This E field is what we call the Hall effect, okay? So because you have in a B field current flowing, it generates an electric field that causes the charges to go from one side to the other. So all the current forces the electrons to go up here, and the holes go to here. So it pushes. It's like driving in Britain or the United States. Okay, so it depends on if you're the electron or if you're the positron. But one way or the other, you're driving. If you're the electron, you're on the left side of the road, which is Britain. If you're the hole, you're on the left side of the road, which is also Britain. This is basically driving in Britain, what I've just drawn. Okay, so I think you guys get it. Let me just say all our positive charges are going this direction, all our negative charges are going in this direction. And that's just the nature of this situation. If we flip the B field, all of that flips, or if we flip the current, all of that flips. Okay. So let's talk about what happens. We've got the force of the electric field is equal to the charge times the electric field. And that electric field happens to be a result of, our force happens to be a result of the charge moving in a certain velocity, B. So we put these two things together. What is that velocity? We talked about it before. It's our drift velocity. So we can then put these two things together. We've got E Hall. I better put Hall here. And then EV B, but that's our drift velocity. So you can solve for the drift velocity, and then you end up with your E field, I'm going to put Hall here, over the B field. And that works. So we like that equation. This is only after it balances. So we're not talking about current ramping up. We're talking about a constant current. So I has to be constant for this to occur. Okay? So more on the Hall effect. Our current is equal to the number of electrons times the drift velocity times some area, A, that it's traveling through. And that equals our number of electrons. And then the drift velocity is E Hall over B. And then we're going to multiply that by our A. Now, the E Hall is equal to our, if we multiply L times it, and then we have this whole thing going some distance L. Okay, so our negative charges are marching along this distance L. Our positives going the other way. And we get that that is, of course, our voltage. So that gives us that our E Hall is equal to our voltage over L. Now we can substitute that in. All right. So our current is equal to our NE voltage over L, area over B. And we can solve that for our voltage. What is our voltage from one side to the other? This voltage. What is that voltage? We can do this. So we say, okay, ILB, I'm just doing this equation right here. ILB divided by N times the charge times V and A. So, I'm solving for V. So, okay. ILB N E A. Okay, so the upper edge, or I'm sorry, the bottom edge is V plus. The top edge is V minus. And now we can then say, all right, we can take two equations. Which two equations? This equation and this equation. And we can give our sense of N times E times A that equals I B L over V in one equation. And then in the other equation, we've got I over our drift velocity. This is voltage, by the way. and this is drift velocity. I need to keep my velocities as a small v and make that a smaller d. So that is an equation that we can use. But of course, we can solve this for the Hall voltage. And the i's cancel. So we have our Hall voltage is equal to our drift velocity times our B field times the length of our so this makes it really easy. So we've got this thing, we've got the length. Oh, I said it was I said the length was this way, and I'm sorry. This is not the length. Gosh. This is the length right there. So that's my length, and we have now figured out what our voltage is due to the velocity of the electrons flowing, okay, their velocity, their drift velocity, and the B field that it happens to be sitting in. Those are the only things that we need to get our Hall voltage, okay? So that's all you need to know, and you're set. Okay, I'm going to end with this and post it, and then I want to talk a little bit more about this. Okay, I'm not going to end yet. We just have, give me 5 minutes. Okay. So I don't know if you guys know about a mass spectrometer, but mass spectrometers are really nice. We've got B fields. I'll draw the B field situation into the page. So imagine the whole region in here is B field, okay? And we've got some thing that is spitting out charged particles, okay? And they're coming in with some velocity. And they're going into this B field. Should we make the charged particles positive or negative? I don't know. It doesn't matter. But since I've got them going like this, they're going to go in this direction. Okay, they're going to curve in this B field. And that curve is going to be some radius. And over here, we'll have some detector. Okay, and the detector has bins in it. So the way I've drawn it, this particle is going to end up in this bin. Okay. A lighter particle or a particle with a different charge or whatever is going to end up in this bin. Or some of the particles are going to end up in this bin. And that's how we can tell the difference between some things or other things. And so how do we come up with this radius? Q, okay, so V is my current. It's going in that direction. The force is going in, so V cross B, force is going in. So Q is positive. Okay, so let's just say it's a, it doesn't matter. It's a plus Q. Okay, Q is plus Q. And we've got our B field, and it turns out that our radius is equal to the mass of the particle divided by the charge of the particle times the velocity of the particle. I'm going to call it drift velocity, but it's really the VV velocity, okay? So it's definitely the velocity, not voltage, times the B field. And you could go through and derive this if you want. You can figure that. But the mass dictates the radius if the velocity and the B field are always the same, okay? Because the charge isn't going to change for the particle. For instance, we could have a carbon atom that is +1, okay? So carbon +1. That has a certain mass, right? It has a mass of a carbon atom, okay? And it's missing an electron, so big deal. But we could also have a hydrogen that has its electron stripped, and the mass of that hydrogen, these two things have the same charge. Q is the same. So the mass of the particle is going to dictate where or what this radius is, because they're going to be both shot in with the same velocity. They're going to both be shot through a B field, the same B field. So the radius is what's going to change. So one of the things is going to have a larger, obviously the carbon atom is more massive. So since it's more massive, its radius is going to be out here. So that would be the carbon atom going out there. And then the hydrogen atom would come in here. Okay, and there is mass spectroscopy given right there. So I just thought I'd throw that little bit in, mass spectrometer. And it's easy to strip. You'll throw a whole bunch of stuff through this in a gas. You throw it through a field and strip the gas of its electrons. And it's nice because then you have an ability to move those electrons or those atoms minus an electron easier with E fields. So that's a pretty cool thing. All right, so the next time we're going to start talking about chapter 12, and I am going to do that next.